This is a resiliency case study of Talca Province, Chile. Chile is a country in South America. We're going to focus on an area right about here. This is the Maule region, one of 15 administrative divisions within Chile, with a capital called Talca, about 1 million people, and is most famous for the Maule earthquake in 2010 with a magnitude of 8.8. Here's the Maule region with the Talca Province highlighted. Maule region is divided up into 28 communes. We're going to focus on 3 of them. Constitucion is most vulnerable to tsunamis and earthquakes because it's located along the coast and has a high urban population. Talca is the capital of the area and most vulnerable to earthquakes because of its density of buildings. San Clemente is mostly rural, but is very close to volcanic centers. The 8.8 Maule 2010 earthquake was an especially large and damaging event in this area. This event also generated a tsunami, which reached 8.3 meters of inundation in Constitucion. Chile has 90 active volcanoes. The following picture is an example of Cabulco volcano, which erupted in April 2015. The crust of the Earth is divided up into several plates, which are constantly moving and interacting with one another. Along the entire coast of Chile, one plate is moving beneath another. This is called subduction and results in volcanism and earthquakes. Subduction can also sometimes generate tsunamis when the overlying plate is dragged along by the underlying one and then suddenly snaps upwards, raising the sea level above it. Types of volcanic hazards include lava flows, ash falls, pyroclastic flows, lahars, poisonous gases, acid rain, and atmospheric effects, which can raise or lower the atmospheric temperature, which can reduce crop yield, cause disease, and starvation. The eruptive power of a volcano depends on its size and explosivity. VEI, or Volcanic Explosivity Index, is a general measure of this. A VEI of 8 is called a supervolcano, and it has been unseen in human history. Is there a supervolcano in Talca Province? There might be. It's called Laguna del Maule. At first glance, this area looks like a picturesque environment, but beneath there might be a much more destructive power. This is a map of all the eruptive material at Laguna del Maule. Its sheer size makes scientists think that it is most similar to Long Valley supervolcano in California. 169,000 people live within 100 kilometers of Laguna del Maule, or LDM. There is also an energy plant being built right on top of the volcano. In volcanic areas like this, there are 5 steps needed for mitigation: identifying risk, hazard assessment, volcano monitoring, engineering mitigation solutions, and energy response preparation. AVDAS is the Volcano Observatory of Chile, monitoring all 90 volcanoes 24/7. They have created this preliminary hazard map around LDM. They also created ashfall maps by season. However, these predictions are made based on very preliminary knowledge of the volcano. For earlier warning purposes, the University of Chile runs a strong motion seismic network. An array of instruments in the Pacific measuring for sea level change provide early warning of tsunamis as well. A current intensive study at LDM is doing work with volcanic history, uplift rates measured via INSAR and GPS, gravity change, magnetotellurics, and seismic activity. These seek to model the underlying volcanic structure, which may look something like this. The bigger the chamber, the bigger potential eruption. INSAR measurements showed an uplift rate of 25 centimeters per year, which is alarmingly fast, especially when compared to other volcanoes around the world. GPS confirmed these measurements. Gravity is comparatively low above the center of uplift. This is indicative of a low-density material intruding into the area. Magnetotelluric studies have found zones of low resistivity, which may indicate liquid magma. Small local earthquakes seem to be clustered around the southern side of the lake. There was also another seismic study being done called ambient noise tomography, which is indicating low velocity zones beneath the lake, which may be magma centers. Now let's look at Chilean building codes. They mostly serve to make buildings resist moderate seismicity and prevent collapse in large seismicity events. However, these codes are not always enforced. Some tools that could be useful include Aloha for ashfall mapping, interactive inundation maps for tsunamis, and agroclimate to help farmers prepare for volcanically induced famines. The scientific community is responsible for the initial planning stages of strategy. They then must pass on their findings to the government, which can then implement these findings into policies. What can we do now? We already know that LDM is a high-risk volcano, that better maps are needed, and the AVDAS will continue to monitor the situation. Now we need to better enforce the building codes and educate the public. Designing roofs to withstand ash load is important even for buildings on the furthest side of the Talca Province from the volcano. Engineering also allows buildings to withstand earthquakes with elements such as isolation bearings and shear walls. However, we cannot make buildings resistant to all types of hazards and must move to things such as evacuation routes. Building for a supereruption would be quite impractical. This is the 4 levels of alert that AVDAS uses to alert the public when a volcano is becoming active. We must make sure the public knows how to respond to these 4 levels. I recommend that buildings are updated to these new building codes and that scientists and politicians are better connected. If a supereruption were really to occur, the entire Earth could be affected by this event.